So today I'm going to talk about a framework for solving inverse problems where training data or calibration data are used to compute optimal solution methods. Okay, so we'll actually break down the talk into two sections. The first section, I'll give a brief introduction to inverse problems and talk about how we design optimal spectral filters for these types of problems. And then the second half of the talk, I'm going to look at problems where you may not know the forward model, or you may only have an approximation of the forward model. And in that case, you want to design optimal inverse matrices for solving these inverse problems. Now, a lot of this work is joint work with my collaborators Julianne Chung at Virginia Tech, as well as Diane O'Leary at the University of Maryland. So to make sure we kind of all start off on the same page, the first question would be, well, what is an inverse problem, right? So in the most general sense, in order to understand what an inverse problem is, you need a forward model. In that forward model, you're given some input signal, which is affected by some physical system. The output signal is the observation. This is the data that you collect from your devices. And the goal of the inverse problem is to say, given that output signal, as well as some knowledge about that physical system, I want to reconstruct the original input signal. So it's a simple enough idea. Mathematically, we look at it using this linear inverse problem. So here, C is the unknown parameters that we want to reconstruct. A is typically a very large, ill-conditioned matrix that models the forward process. So this is that forward model. Delta is some additive noise in your data, and then of course B is the observation, the observed data. And the goal of the inverse problem is to say, given B as well as A, we want to compute an approximation of C. Now, I want to give you an application to kind of give you some context as to the kinds of problems we're looking at. So in image deblurring or image deconvolution, the basic idea is you're given a blurry image. Okay, so that's your observation B. And you know something about what caused that blur. So for example, you may know something like if you're taking a picture of a satellite out in space, you may have atmospheric blur. If you're taking a picture of the inside of someone's body, then you may have motion blur. Or other types of blur. So all of that is incorporated in this matrix A, and the goal of the problem is to reconstruct a clean image, a non-blurred image. So when we talk about inverse problems, most inverse problems are ill-posed. And what do we mean by ill-posed? So in 1923, Hadamard defined a problem to be ill-posed if a solution does not exist, is not unique, or does not depend continuously on the data. Now I think most of us have a pretty good idea about what the first two conditions mean. In order to illustrate this third condition, I'm going to use that example from image deblurring to show you what it means when we say that the solution does not depend continuously on the data. If you recall, the image deblurring problem, the inverse problem, is to say, given that blurred and noisy image, I want to reconstruct an approximation of the true image. Now, if I use standard techniques that you learn in numerical linear algebra or scientific computing, your numerical courses, to solve this problem, you actually will reconstruct the solution down here. So this is the inverse solution. I just compute essentially A inverse B, right? And then I get this solution. And you can see it looks nothing like the original image that we wanted to reconstruct. And the reason is that there's a little bit of noise in your data, right? Anytime you collect data in real life, you're going to have some noise or some errors. And so during the inversion process, that little bit of error, even though you cannot really see it in the observation, that little bit of error blows up and causes very large errors in the reconstruction. Okay, so this is a common phenomenon. It's seen in a lot of different inverse problems. And so what people do is they include something called regularization. So regularization is just a fancy word for incorporating prior knowledge about your problem. So you may have prior knowledge in the form of noise. So if you go back to, let's see here, so this kind of delta component here. So you may know something about that noise. You may know something about the statistics of it, the distribution of it, the noise level, things like that. And so you could incorporate that information when you're trying to solve your inverse problem. In addition, you may have some prior information about your solution. Okay, so oftentimes we assume something about the smoothness of the solution, the sparsity of the solution. Maybe you want to impose some constraints on that solution, like it's non-negative or it has some bounds. But another approach is that you may think, okay, I know my solution comes from some distribution. So I include some probability information. And that is kind of the goal of this work. So the goal of the methods I'm going to talk about today are to incorporate probability or probabilistic information in the form of this training data that is given to us. And we're going to look at two different types of problems. We're first going to look at computing optimal spectral filters for problems where we know the forward model and we have some nice properties of the forward model. And then in the second half of the talk, I'm going to talk about, well, what happens if we don't know the forward model? Then how can we still compute optimal methods, optimal solution methods? So a really quick outline of my talk. So we have the two big components. We'll talk about, give you a background on spectral filtering, how do we compute optimal filters, and show you some results. Then we're going to look at the second case where we are looking for inverse matrices, regularized inverse matrices, in particular low-rank regularized inverse matrices, and I'll give you some motivation as to why we consider the low-rank case, and then talk about some theoretical results in the Bayes framework as well as some numerical results for the empirical Bayes. So I'll go into the details of that. So to start off, spectral filtering. When you talk about ill-posed inverse problems, there's an important tool, the singular value decomposition, which allows you to know a lot of things about what's going on with your problem. So if I take my forward model, my A matrix, and I look at the singular value decomposition here, where the sigma is just the diagonal matrix with these singular values sorted, and U and V are both orthogonal matrices. Now, the specific properties are that for ill-posed inverse problems, what do we have? If we look at these singular values, they decay to 0 and they cluster at 0. Okay, so you have a lot of small singular values close to 0. Furthermore, if you plot those singular values, you actually can see that there's no gap separating the large singular values and the small singular values. So there's no real concept of a numerical rank in this case. And lastly, if you look at the singular vectors, so the U and V vectors that correspond to the small singular values, those are highly oscillatory vectors. Now, why is this important? So when you write down the inverse solution, I'll go ahead and put it here. When you write down the inverse solution, it's essentially this without the phi. So the inverse solution is everything except this phi here. You see that what you do is you're actually dividing by singular values here. Okay, so for those small singular values, you're dividing by a very small number. Now that wouldn't be so bad, except for the fact that, if you remember, the singular vectors corresponding to the small singular values are highly oscillatory. So what you're doing is you're dividing by a very small number here, causing large coefficients, and you're multiplying it by these very highly oscillatory singular vectors, causing that inverse solution that I showed you in the very beginning, right? The one that was just contaminated with noise. So what people have done is they've considered filtering, spectral filtering, as a way to alleviate this. And the idea is now to introduce a filter factor phi, or phi here. And so we're going to say for those large singular values, right, the good ones, we're going to use filter factors close to 1. And for the small singular values, the ones that are giving us problems, well, let's just cut them out, right? Let's essentially set them to 0. And that is the basic idea of the truncated SVD approach. So here on the right, we show the filter factors for TSVD, and you can see this black line. For the small singular values, you give it a filter factor of 0. For the large singular values, you give it a filter factor of 1. Okay, that's the basic idea. And there have been some generalizations of this idea in terms of the Tikhonov regularization, another well-known and popular method for regularization, where rather than kind of doing this step function, you do a smoother function for your filter factors. Now, an interesting point that I want to make at this point, which will come up later, is that oftentimes you see the filter solution written in this form. Okay, but it turns out by just doing some algebraic manipulations, matrix manipulations, you can actually write the solution as a linear function of the filter factors. So you see it's linear in the vector of filter factors. Now I'll point out later why this is important. You don't usually see this representation for the filter solution, but it will become important in what we want to do. Okay, so these are two possibilities for defining your filter factors, right? Either doing TSVD or Tikhonov. But it turns out, I mean, there are other possibilities as well. And so we've looked at other things like the error filter or the spline filter. So what is the idea here? So with the truncated SVD and Tikhonov filter, the filter factors, all of the filter factors depend on one parameter, this alpha parameter. Okay, so you choose one parameter alpha, and that gives you all n filter factors, okay, by this functional representation. The error filter says, well, I don't want to have all of the filter factors depend on only one parameter. Let's allow, for example, with the error filter, we allow n different regularization parameters. So every single, if I go back to this plot here, every single singular value can have a different filter factor, right? Completely independent of the others. Okay. Then there's something called a spline filter, where we essentially try to fit a spline through the filter factor function, and in that case, we reduce the number of parameters that we need to estimate. Okay, so the big question is, how do you choose alpha, right? So there's been a lot of research on how do you efficiently and accurately get a good regularization parameter alpha. And if you only have one parameter, like in the TSVD or Tikhonov case, there are many approaches out there. I just mentioned two of them here: discrepancy principle and generalized cross-validation, as ways to select a regularization parameter. But what is it that we want to do, right? So what we want to do is we want to kind of generalize this idea and say, I want to compute optimal parameters, and I'm going to use training data to be able to do that. Okay, so what we do is we reformulate the problem so that we can use stochastic programming or stochastic optimization to compute these optimal filters, these optimal parameters or optimal filters, and we're going to use training data in order to do this. Now, this idea, I want to mention, this idea has been rooted in statistical learning theory, in optimal experimental design, in stochastic optimization. So it's not new in the sense that the idea is not new, but applying it to computing optimal filters is. And so here are some references if you're interested in kind of some of the literature. Okay, so we want to compute optimal parameters, right? Optimal parameters are optimal filter factors. How do we do that? Well, we have to build up a framework, right? And so to start off, let's assume that we have a set of signals, let's call it psi here, and a set of noise samples. Okay. Now, if we just select one signal and one noise sample, right, then we can look at our inverse problem. This looks very familiar, right, from the first slide. This is our deterministic inverse problem, right, because I only have one realization of the signals and one realization of the noise. So this is my deterministic inverse problem. But for that one problem, I can define the error, right? Because what do I mean by optimal? I have to minimize some error. So the error in that case is going to be the difference between the reconstruction and the truth. And you can define the error function in various ways. So we're going to define it with this rho function. Okay. The simplest case is to think about it as a norm. So you can use, for example, the p norm, or if you like, the 2 norm of the error. And what is the idea is that we want to compute these optimal parameters alpha that minimize the errors over the entire set of signals and over the entire set of noise. Okay, so this is the idea. Now, of course, we would like to have kind of an infinite number of these realizations, in which case we would be in the Bayes risk framework. So ideally, we would like to compute the parameters that would minimize the expected value over all possible signals and over all possible noise, minimize the expected value of the errors. Right? But it turns out solving this problem is extremely difficult. So number one, you have to evaluate this expected value. Perhaps you may not even know the distributions for your probability distributions for your delta and psi. Okay, so what's typically done is to use a Monte Carlo sampling approach, where you kind of draw realizations. So if you do know, or if you want to assume something about your probability distributions, then you can use Monte Carlo to draw these samples. Otherwise, what we kind of in the context that we were thinking of is that you don't know in advance these probability distributions, but you do have training data. Okay, so we're going to assume that those training data are realizations of some probability distribution. Okay, so here's the framework. Here's the idea. I have my training data, right? I have my k realizations of the solutions and k realizations of the noise. And I want to then, rather than solve the Bayes risk problem, where I'm trying to minimize the expected value of the errors, I approximate the expected value with the sample mean, so the average here. over all of my k realizations. And I'm going to look for the filters, the filters, or you could think about it as the regularization parameters that minimize this average error. So it all reduces to a simple optimization problem, right? So at the end of the day, what are we doing? We're saying, given our training data, we want to find the parameters that minimize this average error. Okay, so we have a couple of suggested optimization methods. We don't claim that these are the best, but they're suggestions. So you can think about, in our framework, we can actually choose any error function we like. You could use p-norms, for example. P equals to 2, or p between 1 and 2, or p is 1 or infinity, something like that. And you could choose any filter factor representation that you want as well. You could use TSVD, Tikhonov, the error filter, or the spline filter. All of them can be used in our framework, okay? But at the end of the day, we still have to solve this optimization problem. So what we propose is for TSVD, because you're really only looking for that index where you need to truncate, right? So it's essentially a discrete optimization algorithm that you should be using. For those problems, we propose or suggest a discrete golden section search algorithm. For p equals to infinity or p equals to 1, you can actually recast your problem as a constrained optimization problem and use interior point methods. So we propose to do that, but we do say that there is a caveat here, which is that when you do reformulate your problem as a constrained optimization problem, you increase the number of unknowns and you increase the number of constraints that you have to deal with. So it's a very large, difficult problem to deal with. So you have to be careful with that. And for the other cases, we actually propose the Gauss-Newton approach, except for this special case right here, where if you use an error filter along with the 2 norm, you actually can solve this problem very efficiently just by least squares. Okay, so and that will come out in the next 2 slides. So we want to do a Gauss-Newton optimization. We need to compute the derivatives, right? So we need to compute that Jacobian matrix. This is where it was important that we look at a different formulation for our filtered solution. Remember, I was mentioning earlier that the filter solution can be written as a linear function of the filter factors. This is when it becomes important, because then when you take the derivatives, here the Jacobian is fairly simple to compute. So here phi of alpha just contains those partial derivatives with respect to your regularization parameters. And of course, you can compute the gradient and Gauss-Newton approximation of the Hessian. Now, for the 2 norm, things simplify very nicely, because for the 2 norm as well as for the error filter, things simplify because your filter factors, right? You have n filter factors that you're solving for. So actually, your derivative here is essentially just identity matrix. Okay, and then here as well, the decay kind of disappears, and that's why you get a linear system. Now, another kind of important thing that we saw was that if you look specifically at the 2 norm, okay, and if you have some assumptions about your probability distribution, so if, for example, you assume that the noise, the delta, the noise, comes from some normal distribution with 0 mean and variance beta delta, let's say, and we use the error filter in that case, then it turns out, what are we doing? We're essentially solving for the Wiener filter. If you've heard of Wiener filter, maybe in some signal processing framework. And then in addition, if you assume something about your data, so these are your realizations, your size, in our case, in our training images. If we assume that those also come from a normal distribution with certain properties, then we actually find out that what are we actually computing? We're computing the Tikhonov filter factors with a particular regularization parameter here defined by the noise to signal ratio. So why is this important? Because so many people use Tikhonov regularization in their research, in their kind of daily lives, without realizing what are the underlying assumptions you're making. Okay, and so this is why it's kind of important to make this point, which is that when you use Tikhonov, what you're doing is you're essentially assuming that your noise comes from some normal distribution, which is actually not too far off. Usually you can accurately model the noise in that way. But you're also assuming that your unknowns also come from a normal distribution. And so if you think about it in terms of, for example, image processing, where your size represent the different images, this assumption doesn't really hold, right? So if you take a bunch of MRI images, if you take many MRI images, it's very unlikely that they will be normally distributed. Okay. All right, so let me give you some results. So we looked at two different problems. We did a 1D deconvolution problem and then a 2D one. So in the 1D problem, we used this convolution kernel here. Kind of looks a little bit funny, but we used columns of these images for training. Okay, so and we obtained these blurred images here. So this generates our training data. Then we have a different set of images that we use for validation, right? So using these training images, we were able to compute the optimal different methods. So we computed the optimal Tikhonov parameter, the optimal error parameter. So remember, this one depends on only one regularization parameter. This one depends on n regularization parameters. And we wanted to compare it to standard methods, things that are being computed kind of as state of the art. And that's something called, remember I mentioned the generalized cross-validation method, so you could use that to estimate your regularization parameter. Or if you have the true solution, you could compute the TIC-MSC, which essentially finds the parameter which minimizes the error between the reconstruction and the truth. Okay, so we had 600 training signals. So we evaluated on 2,800 validation signals, because oftentimes in real life your noise level is not fixed, right? So if you run an experiment many times, the noise level may change. We actually allow a range of noise levels, and we randomly select a noise level between them. Okay, to kind of mimic what would really be going on in an experimental situation. And here on the right, what I'm showing are the errors, the reconstruction errors for the validation data. Okay, so these are box plots. The center line of all of these box plots correspond to the median reconstruction error. So right, I have 2,800 validation signals, and of those 2,800 signals, the median reconstruction error is represented by this line here. The box edges correspond to the 25th and 75th percentile. The lines go out to the extreme data points, and then all of these dots are just extreme outliers. Okay, so it's just a way to statistically evaluate the methods. And what do we see? So in general, so let's first look at the standard methods. So TIC-GCV, remember, is using Tikhonov regularization with generalized cross-validation. So overall, it doesn't do so well because the average reconstruction or the reconstruction errors are quite large. TIC-MSC is using Tikhonov regularization, but using the optimal parameter choice. So this one in real life we cannot get because it requires the true solution. Right? So we cannot get this one, but at least we want to put it up here so that we can compare. So this is essentially the best you can get with Tikhonov. Now, these two here use training data. Okay, so the first one here, opt-TIC, still requires that you use a Tikhonov formulation, right, a Tikhonov function, but the regularization parameter is selected by minimizing the errors over all the training data. And you can see that it does pretty well because it pretty much compares with this TIC-MSC approach. Now the last point I want to make is for the opt error. So this one uses training data, but allows n different regularization parameters. So it allows every filter factor to be different. Okay, and in that case, you can actually get better reconstructions, even better than say the TIC-MSC, because you allow those more degrees of freedom. Now I have to tell you, you have to be careful though, because for the opt error to work, you have to have enough training data, right? Because in all of the Tikhonov cases, you actually only have one unknown, that one regularization parameter, right? That defines all of the filter factors. In the opt error case, you actually have n regularization parameters that you're having to solve for, right? So So you just have to be careful, make sure you have enough training signals to be able to learn a good set of filter factors. Okay, so now I want to show you for the 2D case. This one is actually very enlightening because you can a lot of features come through. So what we did is we took a bunch of satellite images from NASA's website. So we took 800 training images, and then we took different, so these are some examples of the training images, and we did random rotations, translations, and other manipulations of these images to get 800 of them. And then we took 800 different satellite images and did the random rotations, translations, and that formed our validation set. We blurred everything with a Gaussian point spread function. We chose noise levels between 0.1 and 0.15, and we compared different things. Okay, so in this case, we looked at an optimal TSVD filter, an optimal Tikhonov filter. So both of these rely on one regularization parameter. We looked at an optimal spline and an optimal error filter. So both of these require more unknowns, but all of them use training data. I'm not going to talk about the smooth one. It's essentially assuming that your filter factor should be smooth, but I won't go into the details of that. And then we look at different error functions. So if you remember, I said you could use the 2 norm, right? You can minimize the 2 norm of the error, but you can actually do other things as well, because you may want to minimize, say, the 1 norm of the error or the infinity norm of the error, right? And so for this case, we actually use the Huber function as our error function. The Huber function is just an approximation of the 1 norm, because with the 1 norm, you know you have non-differentiability at 0. So you essentially use some smoothing with the Huber function to get rid of that problem. So this one, the Huber function essentially approximates the 1 norm. We're going to look at the 2 norm case, and then we're going to look at the 4 norm case, because 4 approximates infinity. So we're trying, well, I mean, for these problems, we cannot do the infinity norm because the problem just gets too big, so we're going to use some approximation. Yeah, you have a question?
So the noise level 0.1 to 0.15, it's an independent Gaussian noise on each case?
Yes, thank you. It is just Gaussian noise, Gaussian white noise that's added to the images. Yeah, thank you. I forgot to mention that. Okay, so we want to look at how these optimal filters or optimal parameters perform. All right, so again, we're looking at box plots. Let's actually just pick out one of these first. So let's look at the 2 norm case right here in the middle. These are the different methods. So opt-TSVD, opt-TIC, opt-spline, opt-error, and smooth. And what you see is that, again, by allowing more degrees of freedom, so that with the opt-spline and opt-error cases, you can get on average, or in general, smaller reconstruction errors than you can get with the standard methods, even when you're using the training data. Okay, and this kind of trend is seen throughout all of the different error functions. Now, we actually wanted to compare a variety of things. So first of all, we wanted to look at those filter factors to see what we were computing. And for these problems, these are the filter factors. The black line should be familiar to you because that was just the TSVD case, right? The red line here is the optimal Tikhonov set of filter factors as a function of the singular values. Now the pink one, kind of the magenta one, is the optimal error filter. So remember, with the optimal error filter, you're allowed to have a different filter factor for every singular value. So there's no functional form, right, for this magenta kind of curve. And you can see it is a little bit jumpy, right, which is why we thought to include the smooth case. But if you use a spline fit through these for the filter factors, you get this kind of blue line here. Okay, so we definitely can see that the filter factors are affected by the training data. Now, the other interesting thing we saw was that if you look at the error image, so if you look at the reconstructed image and the true image, and you look at that difference in absolute value, and you invert the color map. Okay, so I know that sounds a little crazy, but what we're essentially looking at here are the error images, and everywhere you see black, that corresponds to some error. Okay, everywhere you see white, it means that you reconstructed that pixel very, very well, right? Almost exactly. Okay, so what do we see in these images? It's actually a little bit difficult to see on the projector, but I'll tell you what you would see. So for the Huber function, what you're essentially doing is you're essentially minimizing the one norm of the error, right? And so what that means is that your error image is quite sparse. So in these flat regions where there's not much information going on in the flat regions, you actually get very good reconstructions. It's essentially white, and only around the edges do you really get the errors in your reconstruction. With the 2 norm, it's a little bit more distributed, right? Because you're essentially minimizing the average of the error. And with the 4 norm, what are you doing? You're essentially, if you think about the 4 norm approximating the infinity norm, you're minimizing the maximum error, right? So that means that overall, the errors are distributed everywhere, but in general, all of the errors are small. So these are all on the same scale, so you can kind of compare. Right here, you don't see as much of the black or gray. Okay, so that motivates why we would want to even consider the different norms, why we want to consider the different filter factor functions. Okay, so let me quickly summarize for the first part. So for the optimal filters, getting good regularization parameters can be difficult. Oftentimes, that is where most of the effort is being spent. Okay, so when you're solving inverse problems, getting a good regularization parameters it can be very costly and very time consuming. And so what we propose is to use training data to compute optimal parameters or optimal filters. And it turns out that these filters can be computed offline, right? So given your training data, you can compute all of your optimal filters or optimal regularization parameters. Then when you get a new image from your telescope or your satellite, right, then you just apply it. Okay. And then furthermore, you can have different error measures, different filter representations. All of it can fit within this framework. We actually, since the first paper here in 2011, we've actually extended this idea to problems where you want to do deblurring and denoising, so a 2-step process for image processing, and also looked at cases where you have maybe missing pixels. And so it turns out in both of those cases, an optimal filter framework works nicely. And then more recently, we looked at some extending this idea of optimal filters to problems to general form Tikhonov problems where you have some additional regularization operator in your regularization term. Was there a question? Yes.
Sorry, so if I understood correctly, how you were comparing different filters, the conclusion was that the ones which involve more parameters require more data, but give you a much better recovery.
Exactly.
But on the other hand, the quality of your training really depends on how well the sample corresponds to the underlying distribution in the actual input, right?
Well, yes. I mean, you do have to assume that, for example, if I'm looking at satellite images for my training data, then my validation images should probably also be similar.
But have you found that those filters which require more parameters to be fit are more sensitive to the difference in the distribution of the sample versus the distribution of the entire input space?
So surprisingly not. So what we actually found was that if we used, for example, satellite images to train these filters, right, the optimal error filters, and then we used it for a completely different kind of looking at, say, a picture of flowers, it still did a very good job. Now, why that is, we have some insight, but we are not 100% sure. So I think it has to do with the frequency domain. So what you're essentially doing is you're developing optimal filters that are good for images that can be represented in some frequency domain, whether it's the Fourier domain or the discrete cosine transform or wavelet domain, something like that, right? So as long as you have similarity in images in that particular domain, then your filters should do well. But we don't have, I guess, the theory that would tell you, okay, how far you are from the sample, and still be able to do well. Another question?
So a related question, maybe. So you, in your examples, assumed Gaussian white noise. How robust are your filter choices to that noise model. So
Mm.
if you take
Yeah.
those filters and plug in spectral noise, does it still
Yeah,
look good?
yeah. So we did consider looking at this for Poisson noise as well. The thing you have to be careful about when you do that is that when we write down our filter solution using the SVD, we are actually inherently assuming we have Gaussian white noise, right? Because we know that that solution, the TSVD, for example, solution, is coming from the least squares problem, which assumes the white noise. So it's not, I guess it's not clear, right, if it would do well with other noise types. I mean, we did play around with like Poisson and exponential noise, but I mean, we really didn't see much, a significant deviation from these kinds of results. Yeah. Okay, so that's the first part, right? Talking about how do you compute these optimal filters, and for the next part, it's actually a generalization of this idea. So what happened was we were working on this project, the optimal spectral filters, and then we started thinking, well, one of the disadvantages of this approach is that you need to know A, right? You need to know your forward model. You have to have the matrix A. Furthermore, you have to have the singular value decomposition of A. And for very large scale problems, oftentimes you don't have that. So in image deblurring, if we're reconstructing images of size, say 256 by 256, the size of our A matrix is 65,000 by 65,000. Right? It becomes very large. And unless you assume certain boundary conditions or certain structure or sparsity in A, it may be difficult to get that singular value decomposition. Okay, not to mention getting A itself. So we decided to extend our idea to the case where you don't have A. Okay, you don't have A at all. All you have is training data. You have, think of it as a black box, right? Your system is a black box, and you send in input and you get output. And you can do this over and over and over again, and that constitutes your training data. Okay, so let's get started. So what do we want to do? We don't have A, right? But we want to compute a reconstruction matrix. Okay, so we want to compute some matrix Z such that when I apply that matrix Z to my right-hand side, B, and I look at the error here using some function, again, I can use any function that I want, then I want to minimize this error. So this is the error as a function of Z. I can think of different P norms, for example, or 2 norms if you like. And the basic idea of this project is to find a matrix Z which would minimize the error over all of my training data. Okay, so this is the idea. Now, this is really hard because remember, like I said, A, typically the size of my problem is huge, right? If A is 65,000 by 65,000, that means my matrix Z here, my reconstruction matrix Z, is also 65,000 by 65,000, and the number of unknowns is just too large, right? So you think, okay, what can I do to reduce the number of parameters that I have to reconstruct? Now, you can think about doing a variety of things. If you know something about A, for example, if you know maybe some information about the decomposition of A, you could incorporate that information in Z. But we don't want to assume anything about our A matrix. And oftentimes this is hard because even if A is sparse, it's not necessarily the case that Z would be sparse, right? Or if A has certain structure, it's not necessarily the case that Z would have that same structure. Okay, so what we did was we said, okay, let's assume Z is low rank. All right, so we're going to force our, we call it optimal regularized inverse matrix, ORIM, our matrix Z to be low rank. So rather than minimizing just this problem here over all possible Z's, I restrict the rank to be less than or equal to R. Okay, so this is the problem that we're interested in solving. Now, quickly, let me address why does it even make sense? Why would we consider a low rank inverse matrix? Because, well, the classical example, if you use truncated SVD, this gives you one particular low rank inverse matrix, and we can see that a lower rank will give you a good solution. If you go too high, you actually get the noisy reconstruction. So it makes sense intuitively. Now I want to break this down into 2 different sections. So the first one has to deal with the theoretical side of things, and then the second one has to do with actual numerical methods for computing such a optimal matrix. So let's start with the theory part. So in Bayes risk minimization, you treat your size as random variables with some distribution, delta as well, random variable with some distribution. I'm gonna go a little bit fast through this because it's exactly mimicking kind of the first part of the talk. Then we define our Bayes risk to be the expected value over all possible size and deltas of this error function. This is the same error function from the previous slide. Okay, and so the rank-constrained Bayes risk minimization problem can be written in the following form: minimizing over all Z matrices with rank R, this expected value. Now, let me quickly point out, if you notice, when you talk about it in terms of the Bayes risk in the theoretical case, you actually need to know A. So that's, I guess, a caveat of the Bayes risk problem. But it turns out this is actually a very interesting kind of linear algebra problem. So when we talk about Bayes risk, we really can only talk about the 2 norm, because it's very hard to get theoretical results for any of the other norms. But for the 2 norm, we get some nice properties, and we can kind of follow things through. So this is the problem we want to solve, right? We want to find that matrix Z of low rank. We have to make some assumptions, as always. In this case, we need to assume statistically independence. We need to assume something about the means and the covariance matrices for the different probability distributions. But what we can show is that this objective function that we want to minimize can be written as the sum of 2 Frobenius norm terms here. And if, in addition, you assume something about your covariance matrix for your unknown psi, then you can actually write it down in a much simpler manner, where the kind of the constants come out. So actually, we have results for the general case here, but it's extremely complicated, and I'm not going to present it today. But if you are interested, I can point you to the paper where we do provide the result for the general form. But we're just going to look at this one here, and we're going to look at the Bayes risk minimization problem. So this problem for this particular form. Now, this is a special case, right? This is in the Bayes framework. What it says is that if I want to find a minimizer of this function here, the global minimizer has a special form here, Z hat, which, so here U and V come from the singular vectors of A, and psi R is just a diagonal matrix of, essentially, these are just the Tikhonov filter factors. Okay, so what does this tell me? It tells me that the truncated Tikhonov, so right, it's a truncation because you only go up to R, and it's a Tikhonov form. That particular reconstruction matrix, Z hat, minimizes this problem. So in the Bayes formulation, now it turns out that you don't really usually solve the Bayes problem because, well, number one, that expected value is hard to evaluate. Number two, you have to know the probability distributions, and so for us, this was more of an interesting linear algebra result rather than a practical result. But this is the paper if you want to see the general cases, the result for the general case as well. And as I mentioned, for other cases where rho is not the 2 norm, we don't have any theoretical results. It's a bit complicated to think about that in terms of the Bayes framework. Okay, so now let's get to the empirical problem, right, where you either generate samples using Monte Carlo or use some training data as your samples. So you're given your training data. Same thing as before. You take the expected value and approximate it with the sample average here. And now we want to solve this rank-constrained minimization problem. Now, how do we do that? Well, one thing we can take advantage of is that we know our Z is low rank, right? So therefore, you can write it as a sum of these outer products. And then your problem simplifies such that you're essentially looking for these matrices X and Y rather than that kind of huge matrix Z. And we have an algorithm that like an update approach that can work for general norms as well as for large-scale problems. The basic idea is this. For simplicity, let's just assume rank 1 updates. Okay, so what you're going to do is you have this iterative process, and at each iteration you compute the best rank 1 matrix. For example, if L is equal to 1, the best rank 1 matrix, and then you update your matrix inverse approximation, and then you just continue to go through this loop. So this algorithm is described in a paper that you can actually find on arXiv at the moment. Okay, so that's for general error measures. How do we compute this low rank optimal regularized inverse matrix? We can use this type of approach. Now, it turns out for the 2-norm case, things simplify. Things always simplify for the 2-norm case. So if we're in the empirical-based framework and we have all of our training data and we list them all into these matrices B and C, then our problem simplifies to become one of just minimizing the Frobenius norm of this difference here. And we found that there's actually a closed form solution was discovered in 1986 and then rediscovered in 2007. And it says that the solution to this problem here can be written as this PR times the pseudo inverse of B. So essentially using the singular value decomposition to kind of write down the solution. And so we actually looked at using this type of approach for the 2-norm case. For small to moderate sized problems, it works. For large scale problems, we actually suggest using the update approach because computing these SVDs can become very difficult. Okay, so let me quickly kind of just summarize, and then I'll give you some results. So for the empirical-based problem, the important thing is that you don't need any knowledge of your forward model. Okay, so why is that? As you notice, for example, in the 2-norm case, everything depends on your training data, so your inputs and your outputs. You can think of your inverse problem as a black box that you just send things through. If you want, you can incorporate information, but it's not required. For this approach, you do need to make sure you have enough training data for it to work. One of the nice things is that what you're computing at the end of the day is some matrix, Z hat, right? And so you're doing a lot of work to get this Z hat kind of offline. But once you have it, computing a solution is very easy. You just do a matrix vector multiplication. It's very fast and very easy. And of course, you can use different error measures here. Okay, so here's an example, 2D image deblurring example. We took 6,000 images that we kind of generated ourselves. Each of them was 128 by 128. We used a Gaussian blur, again, Gaussian white noise with different noise levels, and we compared 3 different methods. So the first, well, let's see. Let's start from the bottom. So the ORAM2 is our approach, where we compute that Z matrix, right, the optimal regularized inverse matrix, using the training data. Now, if I had the true A, the true forward model, I could compute the TSVD solution, right? That would give me a low-rank reconstruction matrix. But that requires that I have the actual A. Another idea is to say if I have training data but I don't know A, I could use our framework to first estimate, let's call it A hat, from the training data. Once I get an estimate of my forward model, then I can do my reconstruction using, say, TSVD. Okay, so both of these approaches in red use training data kind of in different ways. But this requires a 2-step process, and this one you just go straight to the inverse matrix. Okay, so we look at the reconstruction errors for the validation data. This is the mean, the average reconstruction errors. And what you see is that, okay, so the black line corresponds to TSVD. This does exactly what we expect, right? So for small ranks, you start to approximate the solution, and then as you include more of those small singular values, right, you start to pick up the noise. The red line corresponds to the optimal regularized inverse matrix, and the nice thing is that you can see you actually can get reconstruction errors which are similar to the TSVD case, even though in this case we don't have to have A. We just need the training data. Now, this one was interesting, the TSVD A hat, right, where we do a 2-step process where we first estimate the approximation for A, and then we use TSVD, and you get this blue line here. So you can see it's actually not a very good approach in this we wanted to look at the distribution, because this is just the average over all of the validation data. So if you take kind of the last point here and you plot the errors for all of the validation data, you actually can see that ORIM2 does a much better job at kind of localizing the reconstruction errors versus the TSVD.
This one doesn't go all the way to the end, because they should cross, right? At some point, the blue and the blue dashed and red should cross.
Yes, if you go far enough,
Yeah.
right, then
Okay.
you're gonna get
Okay,
you should get.
okay.
But I mean, this is already 1,000,
Right.
A rank 1,000, and the problem is, what is it? It's 16,000 by 16,000, right? 128 by 128. So there was no way we could go to the end. But yes, you're right. And then here's some of the reconstructions. So this is one of the validation images, the observation. These are the reconstructions for ORIM2, TSVDA, and TSVDA hat, and the error images, again, in inverted color mapping. So you can see that, sure, TSVDA, can give a good reconstruction, but it requires us to know A. ORIM2 allows us to use training data in lieu of knowing the A matrix, and we were still able to get very good reconstructions. Okay, so to conclude, I've described a new framework for solving inverse problems. We talked about, in both cases, we talked about two different settings. The Bayes problem, which, it gives us some insight into our problem, and some results can be derived specifically for the 2 norm, but in general, the Bayes problem is not really something we want to be solving in real life. The empirical based problem, however, is what we're using. We use either training data or realizations using a Monte Carlo approach, and we can compute optimal spectral filters for when we know A and we know it's SVD. But if we don't know A at all, then we should use the second approach where we look for the optimal low regularized inverse matrix. Now, all of these optimal filters or optimal matrices can be computed offline, which makes it more efficient. That makes the reconstruction more efficient. And we're able to incorporate some probabilistic information in this framework. Now, there are a lot of things that still can be done in terms of different stochastic optimization methods for solving this, different high-performance computing, including additional constraints like sparsity or smoothness, things like that, as future work. So thank you all for your attention, and thanks for sticking around on Friday afternoon and such a nice day. Happy to take questions. Dave? Mm-hmm.
So this is sort of a two-parter, I guess. So you're saying you want to apply this approach when you don't really know the transformation, but for the image processing problem, you know a little bit, right? So you're very likely looking at something where if it's not blurring with a spatially invariant kernel, that's probably at least a good approximation. So the two thoughts that come out of that are, one, if you take both your source and target image and move them into the 2D Fourier domain, it seems pretty likely that you're going to be looking at something that's mostly diagonal.
Well, okay. So it depends what your blur is. So oftentimes, almost all research or talks that you would see on image deblurring assume that you have, say, periodic boundary conditions. In that case, Fourier transform is the perfect frequency to be using, right? So if you do put it into the frequency domain, it should be essentially diagonal. But in reality, you have things like spatially variant blur, where every pixel is blurred by a different point spread function. You have other boundary conditions, of course, than the periodic case. And so in those examples, you cannot use these assumptions, right?
So the secondary question was, in the cases where you can't necessarily assume that, do you still have enough information that you could cook it into your model as a prior? So you're talking about doing Bayesian optimization anyhow. If you do something where you say, I maybe this isn't quite right, but I kind of think this is the right place to start. That might give you, ideally that would give you better results with less training data. If that's something
That's a nice idea. We have not looked at that, but I mean, essentially saying maybe we could use some approximation to build up our.
Right, or just thinking on a probabilistic framework, make that the prior.
Yeah. So actually, so recently, Misha Kilmer, Diane O'Leary, and I looked at kind of this problem where suppose you have an approximation, right? And you want to, and you think about solving your problem using that approximate basis. It turns out it does not do well at all. So the reconstructions that you can get with the approximate subspace is can be very poor compared to, say, using the original subspace. So at the end of the day, it's, even though yes, you're right, you could probably use that information maybe to build up your prior. I think you could not just use that directly to get the reconstruction. But that's a nice idea. Yeah, thank you.
Questions?